Welcome to lesson 2, vectors in the plane. Listen, everyone, I have no clue how long this video is going to be. This could be long. I really don't know. So just be prepared for possibly a doozy here. Okay, we've got vector as our first vocab term. A vector is a quantity with a direction and magnitude. So it's going to be going in a certain direction for a certain length, right? Certain distance that's covering. So right away, we're going to be checking out some vectors, right? We've got vector v right here. They show us starting at 1, 2, and it goes all the way up here to -1, 5. And we got vector u here starts at 3, -2, and goes all the way up to 1, 1. We want to show that they're equal. Well, here's the deal. All right, we can find distance on a coordinate plane by taking the square root of right, if we had x1, y1, x2, y2, if we were looking for u, it'd be the square root of y2 minus y1 squared plus x2 minus x1 squared, right? So we've done this stuff before. This is way back in geometry type material, right? Distance formula. So let's see. This would give us a square root of -3 squared plus square root of 2 squared. So we're coming up with the square root of 13. Now if I want them to be equal, when I check out v, doing the same idea here with the distance formula, I'm going to hope to get that same amount. So for v, we got, let's see, 2 minus 5, and then we got 1 minus -1. I can already see it, and I'm going to get the same thing, right? I'm at the same spot where we are right now, but just to finish it off, we come up with the same thing, right? Square root of 13. So that shows that their direction, or at least their magnitude, is the exact same. Okay, and we can see that they're pointing in the same direction, so they're equal. Okay, they're equal in length. So I want you to try this one here on your own. You don't have to have a coordinate plane drawn for these. You can really just do the math for them right on the side. So pause the video and try that on your own. Alright, let's see how you did. I'm going to find u first. So let's say x1, y1, x2, y2. Right, so 2 minus 3 squared plus 1 minus -4 squared so that's 1 plus 25, which is square root of 26. So let's check out v now. Same idea, x1, y1, x2, y2. So -2 minus -1 squared and 3 minus -2 squared. Let's see. So -1 squared and 5 squared. It's looking like the same exact thing as last time. And if we finish it off, we come up with square root of 26 for both. So we've just shown that those two are equal. Pretty easy, just distance formula. Okay. Now, from here, we're going to be working with our vectors starting at an initial point, right? Our initial point will be right here. It's going to be at the origin from now on. It's going to make them a little bit easier for us to write, right? So if we start at the origin, we automatically know that this is 0, 0, and wherever this thing happens to land, that would be the length and magnitude. So it's actually kind of easier for us to write it in this way as coordinates because it's giving us the direction and, in a sense, the magnitude. We'll be able to calculate the magnitude, that is. Right? So this is how this works. We have our coordinate plane. This is the vector that they're talking about, v1, v2. Right? This is vector v. we would be going out 2 and up 3, which gives us a direction, and again we have a magnitude that we can calculate. So let's check out some more stuff that we can do with vectors. Okay, for all vectors with initial point P, P1, P2, and terminal point Q, Q1, Q2, if we want to write it in component form, which is how a vector kind of usually is written, we're going to subtract Q1 minus P1 and Q2 minus P2. That'll get us the vector. And if we want to find the magnitude, we just take the square root of our V1 squared and V2 squared. Okay, which makes sense because if we looked back at what we saw a second ago, real quick flip there, right? When we're looking at this, if this is the coordinate 2, 3, when we do our subtraction, y2 minus y1, that's 0. So we're just subtracting the same number. So when it's in this form, we don't have to go through all of this first few steps, right? We can just go right to squaring, and adding. That's the nice thing about it. But we got to do this first. We got to get the vector component form, right? So they want us to write in component form and find the magnitude of v, if these are the original points. So here we go. We're going to do Q, which is 2, minus P, which is 3. And then we got to do that again for the I'm sorry, that should be -1. And then we've got the second one, which would be 2 minus 5, right? Q1 minus P1 and Q2 minus P2. So we're coming up with -4 and -3. That's the component form. Then they want us to find the magnitude. So the magnitude is going to be equal to the square root. We already found our V1 and we found our V2, so we just put them under and square them. Square root of 25, we can actually get that amount in our heads, right? The square root of 25 is going to be 5. So our magnitude is 5, and our component form, -4, 3. -3. Okay, so you're going to try one on your own. Pause the video and resume when you're ready to check your solution. Alright. So if we want to find u, we've got to do Q1 minus P1 and then Q2 minus P2. Let's see, that becomes addition, so that should be 5. This also becomes addition, so 8. So that's our component form, 5, 8. And then if we want to find the magnitude of u, square root of 5 squared plus 8 squared. Square root of 25 plus 64, which equals the square root of 89. We'll leave it there. Didn't tell us to round to anything in particular, so that would be a complete solution. Hopefully you came up with those two. Alright, so far vectors not bad. Right, just kind of some quick coordinate math. We have some other stuff that we can do too. Right, we've got vector addition, which if we have a vector u and vector v, if we're adding u and v, we're just going to add their first coordinates and then their second coordinates respectively. Right? And then next we have something called scalar multipliers, where we're going to let k be a real number and we'll have vector u. And what happens is we multiply our scalar times our vector. It's just going to be like multiplying a scalar times a coordinate, where we distribute that scalar into each coordinate. Okay, so it's really nothing crazy difficult. It's something that should make sense in general, right? If we're adding two coordinates, we just add. If we're multiplying by a scalar like we have done in the past with dilations, we just distribute. Okay, if we see a negative, we're just gonna change all the signs, basically distribute -1. So subtraction, pretty much the same thing as addition. All right, so let's check one out. They give us vector v as 10, 4, vector u as -6, 2, and they want to find each of these three things here. All right, so the first one is going to be 3 times u. U is -6, 2. All I have to do basically is just distribute inside, and we get -18 and 6. Okay, pretty simple. Here, v minus u, I'm going to take v's coordinate, 10, and I'm going to subtract u. I do the same thing for the second part here. Subtract. So let's see. This is double negative. That becomes addition. 4 minus 2 here gives us 2. That's our solution. So far, this isn't too bad. All right, we got 2 times 10, 4 plus 3 times -6, 2. Let's see, that would be 20 and 8, -18 and 6. They want us to add, so 20 plus -18 and 8 plus 6. And if we simplify, that gives us 2 and 14. So really, nothing crazy difficult, right? I mean, the rules speak for themselves, I think. So here's one for you to try. You've got a new vector, v and u. I'm going to leave the example from above so that you have something to reference. Pause the video and resume when you're ready to check your solutions. All right, let's see how you did with this. We're using -2 times v, so -2 times -7 and -3. So if we distribute, that becomes +14 and +6. Good there. U minus v, let's see. So we've got 12, 4 minus -7, -3. 12 minus -7. 4 minus -3. We've got some double negatives happening here. So we get 19 and 7 for B. And finally, 2u. That's 2 times 12, 4. Plus -7, -3. If we distribute, 24, 8. And then we add 24 plus -7 and 8 plus -3. That gives us 17, 5. Okay, so the vector addition and scalar multipliers, really nothing too difficult. So, with addition and scalars, there are properties that work pretty much the same way that they do in most math, right? Let's say that we have vectors u, v, and w, and then we have scalars c and d. These properties, which you might want to take a second to write down, we'll go over them real quick, right? If we're adding u plus v, it's going to be equal to v plus u. It doesn't matter. That's just how addition works, right? Commutative property. Well, actually, commutative is over here. But anyways, let's see if we take vector u and we add 0 to it, we're going to get u back. So this 0, by the way, would be 0, comma 0 vector. Associative property happening right here, right? We can add u and v and then w separately, or we could add v and w and u separately. It's not going to make a difference. Here, the inverse property, if we add u and the opposite of u, it's going to give us a 0 vector out. Associative with multiplication, right? C times du is the same as multiplying CD times u. This distribution, right? If we have C plus D times U, we can actually distribute U to each of these. Same here, if we're adding two vectors and we have a scalar, we can distribute. And then here, 1 times U is going to give us U back, if that's what our scalar is. 0 times U will give us this 0 vector back. And then finally, if we want to find the magnitude of a scalar times a vector, we take the absolute value of the scalar times the magnitude. So we just take the absolute value times magnitude. Pretty easy to do. So hopefully you have those written down. If not, pause the video and write them down now. We're going to try out some of these problems down here. Alright, so they give us C as 4, D as 2, V as -5, 2, and they want us to find C times D times V. Right, so that would be 4 times 2 times our vector -5, 2. Right, but what we can do first is we can do this 4 and this 2, which is 8. And then we can distribute. So that would give us -40 and 16. So that happened pretty quick, right? We just took these two things and we used what was shown up here, right? We had the D and the U together, but we said let's multiply these first. Okay? Here we're going to end up distributing, right? We see what's happening up here. We're going to do let's see, 4 times -5, 2 plus 2 times -5, 2. Let's see, -20 plus 8, -10 and 4, and if we add those, -30 and 12. Okay, I skipped one step. I didn't show my addition here, but I do know that I can do addition pretty quickly in my head, so there you go. So you've got some to try on your own. I'll leave, actually they're not going to be that much assistance to you. You're going to be using some of the other properties, so hopefully you have those handy. So pause the video and try these out. Resume when you're ready to check. Alright. Let's see. So we're doing 5 times U, which is 3, -8, plus, oops, I'm sorry, we're going to distribute. So we're going to have the 5 over here as well, -3, 4. So if we distribute here, we get 15, -40. And distribute right here, we get -15, 20. If we add positive and -15, we get 0. And if we add -40 and +20, we get -20. Okay, sorry about that distribution at the beginning. Second problem, I'm going to do my distribution right away. I'm going to make sure of that this time. Right, we get A, which is 3, times U, 3 -8, plus B, which is 5, times U. Okay, we distribute this first time, we get 9 and -24. Distribute here, we get 15 negative 40. And if we combine 9 and 15 is 24. Negative 24, negative 40 is negative 64. So hopefully you got those using those properties. Pretty easy stuff, especially if you had the properties in front of you to use. Now we're going to do a little bit of actual trig, because if you remember, this unit is on trig. I know it doesn't seem like it with this particular lesson. Okay, but here we go. We got some trig stuff happening. They're telling us that if we have tan of an angle is going to be equal to b over a, and cosine of that angle would be our x coordinate, or v1, and sine of that angle will be our v2, as long as we have our vector in this form ai plus or minus bj. Right, now there's ways of getting this into this form that we discussed in class, so if you want to know why are we switching it into this form, you got to be in class to really get that information. But here's the deal, we have another form that we're going to look at. Okay, this is our a term, this is our b term, and if they want us to find the direction angle, we've got some stuff up here that we can work with, right? In particular, angle that works with some sides that we're using. Okay, so let's check out this problem. They want us to find the direction angle of vector v, negative 8, positive 4. Right, so here we go. Tan of whatever angle it is that we're looking for is going to be equal to b, right? This is our b value over our a value. And if we want to do this, we have to do inverse, right? If we're finding that angle, so we're finding tan inverse of negative 4 over 8. If you type that into your calculator, we are going to come up with 26.57. It didn't actually tell us to round to, so 2 decimal places is okay. That's using your calculator. Now we have a problem though, because if we look at where this thing actually is, right, negative 8 and 4 is over here, right? Negative 8, positive 4. So we're over here in quadrant 2. But this is giving us the reference angle, right? When we found tan of theta in the past, we've had to consider where does it fall inside of this coordinate plane. So what we have to do here in order to find the full angle, because what they're giving us right now is 126 over here, right? I'm sorry, 26 rather over here. This is the angle that they found. We have to take 180 and subtract. And that will give us this remaining side. And that comes up to be 153.43 degrees. Okay, so what happened here? We used tan to find, or tan inverse really, to find an angle. But the angle that they gave us, depending on which quadrant, is really a reference angle, which means that the quadrant that we used, we had to think, all right, 180, subtract what we had, that'll give us the angle we're looking for. So you're going to have another one right here to look at, okay, and we'll go through it together. We have A as 16 and B as negative 3. So if we want to find the direction angle, we're doing tan of negative 3 over 16. We're going to do tan inverse. Type that into your calculator right now, and it comes out with 10.62. But let's check out where that actually is. Positive 16, negative 3 is down here. We're looking for this angle. They gave us the reference angle. Well, I'm looking for almost a full circle except for this amount. So that's 360 minus 10.62. And we come up with 349.38 degrees. So that's the angle that this vector is taking, right? It's pointing out here, and the angle going around would be 349.38. So you will have to check out to see where that particular vector lands. We did that both times. And depending on what they give you for a reference angle, you have to either add, subtract, right? Anyways, here's one for you to try. Pause the video and resume when you're ready to check your solution. Alright, for A, they give us -5, and for B, they give us -6. Tan theta is going to be equal to -6 over -5. Those negatives are going to cancel, by the way. And we're going to type in tan inverse of 6 over 5. When you type that in, you should have gotten 50.19 out. Let's see, -5, -6, it's down here. They gave us this reference angle. So we know if we go 180 to here, we also have to travel 50.19 more. More would be addition. So if we want that full angle, we add, and we come up with 230.19 degrees. And there you have it. That's it for lesson number 2. I guess that wasn't that bad. 26 minutes, 27 by the time I'm done actually talking. If you have any questions about what happened on this, leave them on the comments. Maybe somebody out there in the internet world can help you out, or bring them into class, and I'll do what I can to answer them there. Until next time.